So this code, I mean, I did it by example, but this, of course, like holds in general. This code, like, pretty much does everything we need. Like, this new code with the blue add-on indeed maps this to, it maps this to 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Like this. Let's say happily we got this. Okay, and in general, if you do this for like any, if this is and or not code for like f, then by following this recipe of like basically doing this code, toggling the final answer, and then reversing this code, we transform it into new quantum code that effectively does the following. So this new code is, we really wanted to say, like, this new code precisely does if, is palindrome B1 through B4, then toggle C. We would really love to say, like, our new code precisely does this. But it doesn't quite do this because it always introduces these new qubits, W1 through W11. But at least they're always 0. In fact, it precisely accomplishes this. So consider some hypothetical code. Imagine just you had some quantum code that first did if palindrome B1 through B4, then toggle C, and then it created new qubits W1 through WL for no particular reason. Then you could say, this code from line 0 to 23 exactly implements this spec. Now, you were like, this is not exactly the spec that I was shooting for, but hold on for a minute. Although this code does not, start like, although this code does not like, end by creating the new qubits, nevertheless, I mean, if you think about how the behavior of this line 0 through 23, it exactly implements this. Okay? So it's really almost close to what we desire. So now we need to do one more thing, and then we'll have truly accomplished our mission. So let's get back to extracting or measuring. So I told you, like in lecture 2 or something, like the physical rules of like what happens when you do extract all. Like you get all these different outputs depending on the squares of the amplitudes, and then those qubits are destroyed. And this corresponds to taking all your physical, electrons or photons or whatever and putting them into some kind of like physical measuring device that has like a display. And I said, okay, in real life, you could just like, if you have 10 qubits, you could just take like one of them and put it into a measuring device, which kind of implies that there is some meaning to like just not doing extract all, but just extracting like one qubit. And I said, later in the course, I'll tell you the mathematical rules of like what happens if you just do like extract, A3. Today is not that day. It makes it sound like so like mysterious. Like when we eventually do it, we'll be like, it's kind of pretty much what I expected. It's not very mysterious, but still, I'm not going to tell it to you today. What happens when you like just extract one out of a bunch of qubits? But I will tell you one fact about this, which we're going to rely on today and later on that fateful day when I fully explain extract, which again is not like a real great mystery, but when I fully explain it, you'll be like, yes. So let me just tell you this fact now. Okay, so here's a new, forget everything that's on these boards for 1 second. Let me tell you a new fact. If you do the following 2 instructions, if you like introduce 11 new qubits, and then you immediately extract them again, which you can do, that's equivalent to doing nothing. This is equivalent to doing nothing. It's like in real life, when you actually don't just think of this as like hypothetical computer code, but you actually do it, it's like you get out 11 qubits, and you're like, great, now what do I do with them? Like 11 photons. And then it's just like, oh, just put them into a measuring machine and like never look at them again. You're like, okay, I guess I didn't really need to do that. So this is a fact, that you can physically do this, and that if you do this instruction, then this instruction, it's just nothing. Therefore, finally, if I were to add one more line to this code, if I were to add here, let me squeeze it in, 24, extract W1 through W11, then what we just saw that lines 0 through 23 were exactly equivalent to this. So if we add in 24, extract W1 through W11, well, we just saw that if you just do this, then this, it's equivalent to nothing. So this just like kind of cancels out to nothing. And therefore, these lines 0 through 24 are exactly equivalent to this, which is like finally our goal. Okay, so like all these lines starting here, ending here, we did it. Like this is the code for implementing this instruction quantumly. Okay, and I did it in the case of palindrome, but I guess you'll see that like whatever your and or not code is, if your and or not code has like L many lines, then this will have like 2L plus 1 lines. So basically 2L lines. Here like L was 12, and then like this is actually 25 lines because I started with 0. Extract and new qubits are, if you remember way back to like some lecture, these are like very special quantum operations. They're not qubit manipulation operations. They're like the other two special cases. All the qubit manipulation operations like correspond to path diagrams and they have the unitary property. And like extract and new qubits are just some other special cases. So like maybe this is related to like the wording. Like there's no qubit manipulation instructions that can get rid of these. You have to rely on this like one special like outside instruction, extract, to do it. Okay, so I therefore want to say that this thing that was like our main claim is complete. That if you have classical Python code or whatever that computes a Boolean function with one output bit, just 1 second, then you can convert it to quantum code that computes it in this way, like if f of b is then toggle c. And moreover, this transformation preserves efficiency. Like if the Python code like takes t steps, then the and or not code probably takes t or t log t steps, but at worst t squared steps. And so then you get like t squared lines of and or not code, and then this transformation basically doubles the number of lines of code. So it doesn't like crazily, ruin the efficiency. Yep. Great question. The question is like, do we really need to add this many qubits? Well, it always depends on your example, and this is actually part of like the handcrafting. Like here we did it I did it very mechanically. In my brain, I just like, what is the simplest way you do palindrome? And I like produce this. But you're kind of right that like in some sense, if you looked at this code, like you really kind of want to like get W5 somewhere, and then you kind of can forget all about this stuff. You're like, I don't actually care anymore about this. I just need W5, and then I want to do this. So in fact, one thing you could do if you're like really handcrafting, like an old school like 60s hacker who's like, I'm going to try to use the fewest bits possible, you could kind of get to W5. Then you could like undo all the instructions that computed W1, W2, W3, and W4 and reset them to 0. And then you're going to be like, oh, to do this part, I kind of need like 4 more qubits that are like initialized to 0. Hey, I just got like 4 qubits that are like reinitialized to 0, so I can reuse them. So you like reuse these ones and get W10, and then you'd be done. And also, you don't really need W11. So like you can just go directly to C from these two. So like you probably can do this one with just like 1, 2, 3, 4, 5, maybe 6 qubits rather than 11. Now, 2 things. On one hand, that relied on maybe like extra ingenuity. Like I had to, instead of just blindly like take the obvious code and like just do a mechanical recipe to turn into code, like I sort of used ingenuity to like realize I could get rid of some of these W's. So on one hand, that requires, ingenuity. On the other hand, in real life, you could do it because, like, we're in that situation similar to the 60s people were in, where, like, it is practically super important to, like, maybe try to use as few qubits as possible and few instructions as possible. Because, like, right now, it's real hard to, like, have a qubit. So if you can do it with, like, 6 instead of 11, that's, like, real great. By now, with classical computer, we're like, whatever, like, we're going to, like, allocate 11 bits, whatever, allocate 11,000 extra bits, who cares? Like, 11K is nothing. But, like, with quantum computers, we're like, yes, let's try to save it down from 11 to 6. So all of these observations are, like, quite important for practical quantum computing. But for the purpose of this course, we're not going to, like, worry about, like, over-optimizing. Yep? If you, like, do this, and then put some more instructions in here, and then extract, I don't want to say, again, anything can happen, but, like, we'll see what can happen. But the only thing I'm telling you is if you would never actually do this in real life, but if you were to, like, do this and then immediately, like, extract them, like, measure them, it's the same as doing nothing. That's not actually what we did, right? We didn't just, like, do some stuff, then knew the qubits, then extract them. But we did some stuff which is equivalent to this, and therefore deduced that this extract line sort of cancels out this. Actually, I'm going to try to save a little time by doing the next case verbally. That was the most general case now, is when you have a Boolean function that has multiple output bits. So I don't know, like, consider the function that, like, takes in some bits and, like, representing two numbers and, like, adds them or multiplies them or does their GCD. Like, this is a, function that has multiple input bits and multiple output bits. And in this case, we have a spec for what we're trying to do. Like, what we're trying to convert this to is this kind of instruction that's like toggle f of B1 through Bn onto C1 through Cm. Because this is a classical reversible instruction, so it's eligible to be doable with quantum code. And moreover, it does kind of accomplish this. In particular, this is a quantum operation that operates on n plus m qubits. But it does have the property that if, like, C1 through Cm happen to be all zeros, and then you do this instruction, then, like, the result is that B1 through Bn don't change, and, like, the answer is written onto the Cs. Okay, like, maybe, like, another computer sciencey way to, like, write this would be, like, C1 through... This is, like, classically... I wrote this wrong on Piazza because I had a typo, but it's like... you want to, like, XOR this with the answer. Okay, that's kind of like classically what you're doing here. So for this kind of function, I claim similarly, if we have efficient Python code for it, we can get efficient quantum code for doing this operation. And, well, maybe I'll ask you, like, do you have an idea for how to do it? Yeah?
Just like do each bit one by one, like the procedure.
Yeah, if you really want to just, like, black box it, you can just, like, repeat this procedure one by one for each of the m output bits. Like, you can think, like, oh, if I have classical code for f, I can just, like, that returns C1 through Cm, I can just, like, imagine the code that just returns C1. And now that's like a function that has one output bit, and I know, like, I can implement, like, if that bit is 1, then toggle a certain bit. So I'll, like, do that with C1. And then I can take the classical code that accomplishes or outputs the second bit, and I'll do, like, if that second bit is true, then toggle to C2. And I'll take the classical code for outputting the third bit, run it through this procedure, and I'll get, like, if that third bit is 1, then toggle C3. And I can just do that m times. Or you can similarly think, like, okay, well, I'll take the classical code that computes f, I'll convert it to, like, and or not code, and, like, that'll just have, like, m lines at the end that are like C1 is like this w, and C2 colon equals this w, and C3 colon equals that w. And then I'll do the same recipe. I'll, like, convert all to, like, this kind of stuff. And here at the end, like, I'll toggle all the answers onto C1, C2, C3, and so forth. And then I'll reverse all the previous instructions to get rid of the w's. So it's really like basically the same thing. And really, for the most part, you should now just black box in your head like this fact, like, oh, if there's a classical, there's a reasonable classical program for computing this function f, then I can make an efficient quantum subroutine that does this.